this video, we'll talk about what happens when you have multiple issues with an integral that cause it to become improper and how you have to handle those sort of situations. So the main thing to realize for these sorts of problems is that if the integral becomes improper for multiple reasons, you have to handle each one separately. Right? You can't just sort of group them all together and be done all at once. You have to handle each one independently and see how that causes the problem to work. So here's one example. Integral from minus 2 to 3 of 1 over x to the 5 dx. So if you weren't paying attention, you would probably just integrate this problem directly and go, right? This is x to the minus 5, so the antiderivative is 1 over minus 4, x to the minus 4 from minus 2 to 3. You'd plug in numbers and be done, right? You get that for your answer. However, that is incorrect here. Because this integral is improper, because there is a vertical asymptote at 0, which makes this an improper integral problem. So how do we handle this? Well, we have to get 0 as an endpoint to be able to handle the improper integral aspect of it. So what I have to do is split this into two separate integrals, each of which has 0 as an endpoint, and then do an improper integral calculation on both of them separately, not at the same time, and see what that gives me. So I will rewrite the integral from minus 2 to 3 of 1 over x to the 5th dx as the integral from minus 2 up to 0, 1 over x to the 5th dx, plus the integral from 0 to 3 of 1 over x to the 5th dx. Now I'll work these two out separately. So I'll start with the first one, integral minus 2 to r, 1 over x to the 5th dx, is, now we have the antiderivative, negative 1 over 4, x to the minus 4, from minus 2 to r, to negative 1/4, r to the minus 4 minus minus 2 to the minus 4. And now what's going to happen as r goes to 0? Well, as r goes to 0, this blows up, which means this integral, this half of it here, diverges. And if either part of this integral diverges, the whole thing diverges. So therefore, I could stop here and be done and say this integral diverges. I could keep going as well, and if I check this one, I'll get that one also diverges. And there's no cancellation here. If either part diverges, the whole thing diverges. So since this integral diverges, so does the whole thing. So if there's an asymptote, you must split at the asymptote and handle the two parts separately and see what happens. In this case, it gave us that the integral diverged. There are other examples like this one where we'll see a different result. So this one here, you could directly integrate and you'd be like, oh, I'm good. But this is improper as well because of the vertical asymptote at 0. What do? I split this up. So I can split up as the integral from minus 2 to 0 of 1 over x to the 2/5 plus integral from 0 to 1 of 1 over x to the 2/5. And now I'll work these two out separately. So the first one gives me integral from minus 2 to r, 1 over x to the 2/5, which gives me a 5/3 x to the 3/5 from minus 2 to r, which is 5/3 r to the 3/5 minus minus 2 to the 3/5. And now what happens as r goes to 0? Well, as r goes to 0, now it's r to the 3/5, and that goes to 0. That's going to go away. Limit as r goes to 0 from the left. I'm below 0 here. Of this, the r term goes to 0, and so I just get 5/3 minus 2 to the 3/5 with a minus sign. Great, that one converges. Now I can try the second one. And for the second one, I'll get integral from r up to 1 over x to the 2/5, which integrates the same way. This time I go from r to 1, not from minus 2 to r, and I plug in again. 5/3, 1 to the 3/5 is just 1, minus 5/3 r to the 3/5. And again, when I go to 0, it's r to the 3/5, and that goes to 0, so this converges again. Coming to 0 from the right, 5/3 minus 5/3 r to the 3/5 becomes just 5/3, so this also converges. And thus I can now restick them back together to get my final answer. Integral from minus 2 to 1 over x to the 2/5 dx is 5/3 minus 5/3 times minus 2 to the 3/5. And notice that this is what you would have gotten had you directly integrated in the first place. That's what's going to happen with these problems, but you have to make sure that the integrals converge before you do this, because it's highly possible you'll get a number out of this, but if you don't know that they converge, the answer is not right. The area under there is actually infinite, but you got a number out of it for the wrong reason because you assumed it converged to do the integral without checking that fact first. One other case where this sort of issue can come up is in a problem like the following: integral from minus infinity to infinity of 1 over 1 plus x squared dx. Basically, the point being, I now have two issues here. Minus infinity is an issue, and infinity is an issue, and I have to handle these two things separately. And again, if either one diverges, the whole thing diverges. So let's split this at 0, because that's a convenient place to split the integral, and work it from there. This becomes integral from minus infinity up to 0 of 1 over 1 plus x squared dx, plus integral from 0 to infinity of the same thing. Now let's handle these separately. Integral from r up to 0 of 1 over 1 plus x squared dx. That integral is arctangent, inverse tangent of x from r to 0. And this is inverse tangent of 0 minus inverse tangent of r. Inverse tangent of 0 is 0, so that's gone. And what happens to inverse tangent as I send its argument to minus infinity? Well, that goes to minus pi over 2. The graph of inverse tangent, right, is something like this, where this goes to minus pi over 2 and this goes to pi over 2. So when I limit r to minus infinity of negative inverse tangent of r, I get pi over 2. So this integral converges, and we'll see the other one also converges by a very similar argument. Integral from 0 to r, 1 over 1 plus x squared dx, becomes inverse tangent again from 0 to r, which is inverse tan of r minus inverse tan of 0, and this is 0 again. And as r goes to infinity, inverse tangent goes to positive pi over 2. Limit r goes to infinity, inverse tan of r goes to pi over 2. Means this also converges. And so then my total integral is adding these two together, which gives me pi. And so the point here is, for this one, you probably would have gotten it either way. But there are other cases where the integral will actually diverge if you take care of each part separately. And you have to do each part separately to solve these problems out correctly. So for every issue you see, whether it's an asymptote or an infinite limit on the integral, you have to break off that piece and handle that improper integral separately to decide if it converges or diverges. And then only if all the little parts all converge can you then add them together to get the whole thing converges to a number. If any one of them diverges, then the whole thing diverges and you are done with the problem at that point. So that's with multiple issues. Take them all apart, deal with them separately, and analyze conversion divergence there when you're handling these sorts of improper integrals.